Thank you for attending. This will be the least technical session you've gone to, which might be enjoyable. We are going to talk briefly about the Hernando de Soto Bridge, which obviously had some difficulties, and we were part of helping repair the bridge. With that said, my real question to everyone is, why structural health monitoring? What's in it for you? So there are just 4 different reasons, and what I would like to start with is an analogy where everyone here has a smartphone or some kind of a phone, and it's probably the most powerful tool in our day. The most powerful thing on the phone, however, is the least expensive thing on the phone. If anybody has ever left their phone outside in the sun for more than 10 minutes, the phone overheats and shuts off. If there wasn't a little heat sensor in the phone, your phone would be dead, fried, and phones run anywhere from $800 to $1,700. So the least expensive part of the phone is the most important. That's how I think structural health monitoring is for us today. Years back, it was a research tool. It has come full circle from that point to where now I would say every state, every agency in the country has used sensors to some extent. Resensys is who I represent. However, if you walk into the exhibit area, in all fairness, there are at least 3 manufacturers of sensors. The sensors themselves are of such high caliber and quality that you can literally measure putting a coffee mug on a table. You don't really need that much information, but that's just how good the sensing capability of pretty much all sensors are today. Resensys, this is the strain gauge. That's it. This little object right here. It gets glued onto a bridge. It sends a signal to this, which then goes to another gateway, which can manage 250 sensors and right to your phone or your computer or whatever you want to see the information on. And so with that, I'll start the presentation. I'll try to stop looking over at the board and look at the computer here. There are 4 reasons that most people use sensors, and the first is to monitor an existing issue or problem. So I'm sure every owner has had a crack on a bridge. They want to put a displacement sensor on it to monitor it to see if the crack is growing. The second reason that you should be interested is that you can develop preventative maintenance strategies based on the information that you get. And that's one of the things, that is what I'm going to talk about today. The third is a future endeavor, and that is that AI is coming, and even the computing capability that we have now, you can get a lot of predictive analysis from different types of sensors. And finally, if you have sensors on your bridge, you've greatly reduced your risk of a catastrophic incident. So this project, this session is basically just a quick overview of what happened on the Hernando de Soto Bridge, located in Tennessee. It's about 9,500 feet, so it's a pretty big bridge, 4-lane highway, connects downtown Memphis with West Memphis, carries 60,000 people, is a major evacuation route, and it's pretty much the lifeblood of the city. The fracture was discovered, and that's actually a picture of the fracture, was discovered on May 11th. It was a partial fracture of a tie girder, obviously an important function or feature of a fracture critical bridge. And it was It was observed right at a welded plate. This is the phone call you never want to get. I won't read it out loud, but that was on 911 that the bridge inspector called it in on. So that's what we're all here trying to avoid. You never want to have to make that phone call or get that phone call. So immediately upon getting the phone call, they started to set up, well, I think the first thing they did was call every smart person that they know, and then start traffic diversions. The bridge was closed for 3 months at an estimated cost of $2 to $3 million a day. Pretty substantial economic impact. Emergency repairs were started. Before they could start, they called us and we came out and started to install sensors. This is the sensor. This is kind of the specification for the sensor and for all of the Resensys different types of sensors, and we do have a full suite of every sensor you could imagine. So we offer a maintenance-free, wireless, low power. The sensors require 4 million times less than a 40 watt bulb, which is how we get to a 10-year guaranteed battery life. They're very small, as I showed you. They mount typically with an adhesive, fully weatherproof, provide real-time data with a high sampling rate, and all sensors also report the temperature and their battery life. So as you look on your phone or on your computer, all of that information is provided there for you. This is how the system works. So the sensor, as I said, reports to this little node, which then goes to a gateway, which is solar powered. From there, it goes up into the cloud and then to your laptop, phone, or whatever you'd like it to go to. So we are continuously monitoring everything that occurs on the bridge. It will detect detecting overstrain and all strain, actually. So the system is constantly monitoring itself, is monitoring the bridge, and what happens is that you set thresholds. Every time a threshold is breached, it sends an alert. So you don't have miles and miles of data on your computer at all times. You can go back into your system. If you wanted to call up everything that happened for the last 5 years, you could easily do that and see every single thing that's there. But typically, we don't bother you unless there's something that you should pay attention to. It was kind of, obviously, there was a lot of stress, emotional stress on the project. So this is actually the layout of where all of the instrumentation was placed. There were 44 sensors put on the bridge, and they were installed in less than 24 hours. And if you saw the bridge, it's not like you could just walk up to them, so a lot of work had to be done to get to them, but that's just how quickly the sensors can be installed. In addition, we put in 2 Cinemax because we wanted to make sure that the information coming from them was crystal clear because it was so sensitive. There's no need for calibration, no need for electricity, for communication. So it's very, very simple and straightforward. In most of this, I wouldn't say most, in several states where we have statewide contracts, the maintenance engineers have taken charge of the system. Most of the sensors are completely reusable. They take them from one bridge to another bridge when they want, and they just install them themselves and just start using them. This is just a sample of the data that was collected on the bridge. And interesting, well, What it doesn't show you is that the signature has been completely altered by the cracking of this beam. But what we're showing there is that nothing additionally bad is happening at this very moment, because the changes in the sensors there is all due to temperature. So it's actually in inverse. So when it's colder, the blue, it goes down. When it's hot, it comes up. But they all meet back in the middle, and it's temperature related. What we're looking for, though, as I mentioned earlier, is threshold alerts. And so you can see the circled area where you get pinging or accelerated tension. And at that point, the system goes into overdrive and records an enormous amount, thousands of times in a second, as opposed to at a slower rate when nothing is really happening. So the way the system works is that it is always recording the data, but it doesn't share the data when there's nothing happening unless you say, I want to see it, and then it'll share all of the information with you. It was a very effective, so based on the fact that they now had sensors all over the bridge, it was determined that no vehicles could be on the bridge, or there would be a pretty decent chance that the bridge might collapse, or I won't go that far, that there would be additional damage to the bridge. So the contractor had to come up with some really unique and innovative methods by which to bring the new beams in and fix the structure. And the whole time that they were doing that, they were using the sensors to make sure that nothing else negative was happening on the structure. We do a lot of, industry is changing. I would say, if you asked me 3-4 years ago, I would have said 90% of everything that we did was reactive. So you had an agency had addressed an issue that they'd seen, they wanted to monitor it, and we started to go to work with them. That is really turning around, where I would say it's probably 50-50 now, where people are building new bridges and they're putting sensors on the bridge so that they can develop a signature for their structure. Because as we get further and further along with AI is only going to be as good as the information that you can feed it. And so the more you know about how the structure should behave, the better off you're going to be in doing predictive analysis. So again, some of this is actually repetitive. Strain gauges at critical locations, comprehensive alerts, continual monitoring, and preventative maintenance. Okay, so for me, and I'm more than halfway through already. For me, this is the takeaway. It was a devastating event that took place on the bridge. Anyone who has fracture critical bridges, I would be shocked if you told me you didn't know where your the critical places on the bridge were. And so the price point of sensors has gotten so low that for very inexpensively, you could put a half a dozen sensors on most bridges, know exactly what's happening at those critical junctions, and never have to worry about a crack like that, because the system will tell you pretty much if somebody sneezes on it. I mean, we can monitor the weight of every overweight vehicle. We can monitor the effects of wind gusts on the bridge. We can monitor let's see, for strain, what the weakest areas of the bridge are. So it really becomes quite simple to protect yourself against those types of catastrophic events. I will say that they are continuing to monitor that bridge, and that there is a sister bridge, and they're beginning to monitor that as well. And so that is the lesson to learn. Any of the companies that are here would be happy to give you a general idea of what structural monitoring would cost. The way we work is we sell the system directly to the state, or we work with consultants who provide the locations to the states where the sensors should be. They write reports for the state. Some of the states do it themselves, but it is a very simple and robust system. So since I have a couple minutes more, I decided to go into one additional application, because these are, in my opinion, real-world applications. There's no research required here. And that's bridge deck monitoring. And so we do that all over the place. That is done not with strain gauges, but with both displacement sensors and tilt meters. And so what we typically do is bridges are elastic when they're new. As they get older, they lose their elasticity. As they lose their elasticity, more and more strain is seen on the bridge, which is why they start to deteriorate. So our software, well, this is just a calculation, and if Mehdi was here, he would be, we would spend 10 minutes on this slide. But this is just a formula that is used to look at vertical displacement on bridges, and then really what that means. And I'm more than happy to have that conversation with you at another time, because I'm not that smart. So we can develop a basis by which you can measure the age of your deck and determine how long the deck is going to last by looking at whether or not it's tilting and how much elasticity is left in the deck. These systems are so sensitive that we can tell you when you have potholes on your deck. And so this is actually a data collected, and somebody, you can see on your right-hand side where the accelerometer ticks up, somebody has hit a pothole. And so you can see exactly what that is doing to the bridge and to the deck. This, on the other hand, is just a sample of a tilt meter that is looking at thermal changes. So you have to imagine, these systems measure how your bridge is reacting to the weather. And so I'll say the state, because I won't say what bridge. In Pennsylvania, we actually helped PennDOT because they had a bridge that was heating up on one side and staying very cool on the other side. And the bridge was racking to the point where it was making huge sounds, like, and so we were able to see what was occurring because we had sensors on the bridge. And instead of spending a lot of money to do construction on the bridge, they drilled a couple of holes, and the problem was fixed. Is there anybody from PennDOT that knows what I'm talking about? All right, good. It was a really good job for Pennsylvania. And then finally, our software, which is called SenseScope, has a built-in FFT function which reads natural frequencies and can do analysis for the comparison of bridge decks. Engineers can utilize this data to predict the timing of necessary deck repairs based on the bridge's performance and behavior over time. And that is where we all want to go. You want to be able to say with certainty you know the state of your bridge. And the FHWA has said that if you have systems on your bridge and you can prove that you know what the state of your bridge is, instead of doing a real inspection every 2 years, that can be extended to 3, possibly 4. At the same time, I would say to everyone here, this system will never replace bridge inspection. We consider this as a tool for the inspector. Instead of going up to a bridge and really not knowing what you're looking for, these sensors can provide real information of what is going on the bridge now, and give him some real direction as to where he should be looking. He knows what the weakest area of the bridge is. He can look there. He knows that the tolerances of the strain are still within the design of the bridge, or whether they're not, and then maybe what he needs to do about that in his reporting. As a conclusion, basically structural health monitoring just does this. It detects pattern changes, thermal effects, live loads, and structural changes, and provides quick notification. And it allows agencies and interested engineers to be proactive in their potential use. So I would end by saying the weather is becoming more and more severe and more erratic. We have in the Northeast, we're becoming much more prone to flooding. If you don't know what the state of your bridge was before the flood, you certainly don't know what it is after the flood. If you had this kind of information prior to a flood, you would be able to go up to the bridge, or even during the flooding event, you would know exactly which bridges you needed to attend to immediately and which bridges appeared fine, and maybe which bridges you had some type of an occurrence and you needed to go see them in 3 to 6 months. The same is true for hurricanes. Down south, we're doing a lot of scour monitoring and hurricane monitoring. And so the agencies can actually start to see what the effects of these storms are on their bridge while the event is taking place, and then use their rare assets after the storm to determine which locations they need to go to immediately. And as I said, not technical today. I would just ask you to start thinking about those applications. What keeps you awake at night, and what kind of information would you like to get from your bridges?